Hi everyone. In the last video we examined a situation where we found the electric field due to a bar of charge but at an arbitrary point in the xy plane, and then we moved on to finding the electric field in the situation where that bar of charge was curved into a quarter circle. So that kind of leads us into two-dimensional charge distributions. So here, as a quick example, let's consider a piece of plastic that's uniformly charged, and we break it up into two other pieces of plastic, one bigger, one smaller. How do the surface charge densities of the pieces compare with each other and compare with the original large piece? So is it a situation where the larger piece has greater charge density than any other larger pieces, etc., and you go all the way down? Or does the larger piece that's broken up have a greater charge density than the smaller piece, which is greater than the original? Or is the smaller piece greater than the bigger piece, greater than the original big piece, or are they all the same? So the key term here is surface charge density, amount of charge per unit area. Well, since it's per unit area, breaking them up into smaller areas, you're also breaking them up into smaller amounts of charge. So you're still going to have the same amount of charge per unit area. So the answer is E. How are we going to use this? Well, we need to think about this as we're dealing with surfaces. In other words, in a particular surface, the amount of charge, instead of it being like a linear charge density where the amount of charge in a little piece dx or ds would be equal to lambda times ds, where lambda is the linear charge density, we need to think about the amount of charge in a little bitty piece of area, dA, where that dq would end up being equal to the surface charge density times dA. Now, the symbol for surface charge density that we are going to use is the lowercase Greek letter eta. I think that's a good symbol because a lot of people, in fact most people, use the lowercase Greek letter sigma for this, but sigma is also the symbol that's typically used for conductivity. And some sources use kappa for conductivity, but kappa is basically the universal symbol for the dielectric constant. And those can often come up in the same equation, and surface charge densities and conductivities can sometimes come up in the same equation. So I think just using kappa for dielectric constant, sigma for conductivity, and eta for surface charge density will alleviate a lot of confusion down the road. So that's the convention that I'm going to use. I got that convention from Randall Knight's book on basically university physics, so to speak, but it's a classic book on this, and just calls it physics, but it's physics for scientists and engineers. And I had never seen that convention before, but I think it's a very good convention. In any case, let's consider a ring of charge. So you'll see lots of derivations in lots of different sources, including my students in their textbook, for the electric field down the axis of a ring of charge. So I'm not going to do it. I want to go a little bit farther than that because that's something that's easy to look up. We're going to generalize that, and we're going to do it for a disk of charge. And a disk of charge is also found in a lot of places. So we're going to generalize that still and do it for a disk of charge with a nonlinear charge distribution. So in any case, we can still consider the fact that if you have a ring of charge on that disk, well, how big is a ring? Well, a ring, in this case, is going to have a thickness dr, or delta r. Well, how much little bitty charge is going to be on that practically infinitesimally thin ring of radius r and thickness dr? Well, that would be equal to eta times the area of that ring, or eta dA, but dA would be 2 pi r dr. In other words, the circumference of the ring times its thickness. Now, if the ring was not infinitely thin, if it had a noticeable thickness, you wouldn't be able to do it that way. You'd have to say, oh, well, the area is pi times big R squared minus pi times little r squared. But here, since the ring is effectively infinitely thin, the area of it is just the circumference times the thickness of the ring, the differential thickness of the ring. So here's the example that we're going to use to explore how to utilize our tools. We're going to find the magnitude of the electric field at any point along the axis of a disk of radius big R and charge big Q. But here we're going to make it so that the charge is distributed where its density decreases uniformly from the center of the disk down to 0 at the edge. So, in other words, we have a non-uniform charge distribution. So, the easier example of a uniform charge distribution is in just about any calculus-based physics textbook. So, that's something that you can examine on your own. I'm going to show you how you would do that at a certain point in our example as well, which will end up making things easier. But in any case, the first thing, since it's a non-linear charge distribution, is we're going to need to find out what is the proportionality constant, the equality between our conceptual understanding of this charge distribution and the actual surface charge density. Now, remember, whenever you have a proportion, you can say that your charge density, or whatever it is equal to that thing in the proportion times a constant. So I'm going to call the constant capital B. I don't want to use capital A so that people don't otherwise people might confuse it with the area, and I don't want to use the Coulomb constant K either because, well, that could be confusing also. So the idea is that since the charge density decreases uniformly from the center down to the edge, that means, and we say that it's 0 at the edge, that means that, well, think, at the center it needs to be a maximum, and at the edge it needs to be 0. And this is a linear relationship right here. So we have, or at least the decrease is linear. So we have, okay, plug in R equals 0 for the center. Well, that would be a maximum. Plug in R equals, little r equals big R at the edge. Well, big R minus big R is 0, so that would be a minimum. So, and notice that this definitely decreases uniformly because it's little r to the first power. So what that means is that the surface charge density is equal to big R minus little r times that constant B. Well, what is B? Well, if this was a uniform disk, eta by itself would just be equal to Q over pi big R squared. And that's what we would plug in for eta, just Q over pi big R squared. But here, eta is a function of position from the center of the disk, so we can't do that. Well, how do we find the normalization constant? We use the fact that the total amount of charge in the disk is capital Q. Well, what's capital Q? It's the sum of all of the little q's, of all of the little bits of charge. What's a little bit of charge? Well, a little bit of charge is equal to the surface charge density times the little bit of area. So if you add up all of those areas, so to speak, going from little r equals 0 all the way out to the edge of the disk at big R, then you're going to get your total charge Q. Okay, well, now we have at least a tentative expression for our surface charge density, eta. It's B times big R minus little r. Well, what's dA? Well, what we're going to do is we're going to say, okay, we want to go from the center of this disk to the edge by adding up the amount of charge in a bunch of little rings of thickness dr. So here, in this picture, we have a ring of radius little r, and its thickness is dr. So the area of such a ring would be just its circumference, its length, so to speak, times its thickness. Well, the length, i.e. circumference, is 2 pi r, the thickness is dr, so the area is 2 pi r dr. And now we're ready to pull out some constants. So we pulled out the constant b, we pulled out a 2 pi, and this becomes an easy integral. In other words, just distribute through the little r. So we have big R times little r, and antiderivative of that is, well, it's big R times little r to the first power, so raise the power by 1. So big R times little r to the second power divided by the new power. So big R little r squared over 2. And do the same thing. You have little r squared, antiderivative of that, little r cubed over 3. Now, we are ready to plug in our integration bounds. So plug in the top one first, get the result, and then plug in the bottom one and subtract. Well, you can obviously see that when you plug in the bottom one, you're just going to get 0. So plugging in the top one gives us a big R cubed over 2 minus a big R cubed over 3 inside the parentheses. That's called big R cubed over 6. And 6 is 2 times 3, so you can cancel a factor of 2, and you get pi b big R cubed over 3. Okay, so from that, we solve for the normalization constant. Multiply both sides by 3, divide both sides by pi big R cubed, and there's our normalization constant. Yay! We can just call that b for a while until we get ready to plug it in. So, in any case, though, eta is b times big R minus little r, and here I've plugged in b. Now, how do we figure out the electric field? I mean, what we just did might be part A of a problem on the AP exam. Find the normalization constant, or find the constant B such that the total charge is Q. Okay, so how do we find the electric field? What we're going to do is we're going to calculate the electric field contribution from a bunch of rings. Well, let's consider it from a particular ring. We're going to consider it for a particular ring of radius little r. How far away from such a ring? Well, a distance z from the center of the ring, where I'm having z going up, x to the right, and y into the page. So the radius of my ring is little r. Notice that the radius of my disk is big R, and the distance z above the center is just how far I am above the disk. So we're going to calculate the electric field contribution just due to that ring. Well, here's the thing. Due to symmetry, any components of the electric field, any x components of the electric field from this ring would end up canceling because, say, since x goes to the right, components that are, say, in this area of the ring would end up getting canceled by x components from this area in the ring. Similarly, y components would cancel for the same reason. In other words, y components on the near side of the ring would cancel with y components on the far side of the ring, since I'm saying that y is going into the page. The only thing that's going to be left over is the z components. In other words, all of the off-axis components cancel. So, I'm going to use a little bit of sloppy notation here. So please bear with me with this sloppy notation. I'm going to say that dE is going to be the contribution from each part of our ring. It's going to be the contribution from the entire ring, pretending that we compressed all of it into a little point. So it's something to keep in mind. This dE thing that I'm coming up with here is not a real physical entity. It's something that I'm imagining here. However, since all of the off-axis components cancel, I can come up with a real thing, the electric field contribution in the z direction at this particular point from this particular ring. That's going to be equal to this imaginary dE thing, like if I imagined all of the charge of this ring compressed into a point somewhere on the ring. That'll be equal to that dE times z over curly r. In other words, times the sine of the angle that's above the plane going toward my charge, or sorry, going toward my point. So the sine of that angle, well, that's opposite over hypotenuse. Well, the hypotenuse is the distance from the edge of the ring to the point where I want to know the field. The opposite is called z. So that's just z over what I'm calling curly r. What is curly r? Curly r is the hypotenuse. That's square root of z squared plus little r squared. Remember, little r is the radius of the particular ring that we're examining right now. So yay, now I have the expression for the contribution to the z component, which is the only non-zero component of my electric field at this point, due to this particular ring of radius little r. Well, what is it due to the whole disk? Well, I need to add up the contributions of all of the little rings that have different radii of little r. That is called an integral. That's called an integral. So I add up all of the little dE sub z's. Well, here's the thing. What is that little dE thing without the z subscript to begin with? Well, remember, that was this imaginary entity that I invented as a way for us to visualize exactly what's going on for the z component here, where we imagine that we compress all of the charge in our ring into a point somewhere on the ring. Well, that value for the electric field would just be kq over r squared. Which q, which r? Well, the q would be the dq that's in the ring. The r is going to be the curly r, because it would need to be the distance from where we're imagining our charge being compressed to the point where we want to know the field. That's curly r. That's square root of little r squared plus z squared. So that's basically a Coulomb's law type of thing. Well, we have a distance squared from that, and we also have a distance from the sine angle part as well. So we're going to end up with distance cubed in the denominator there. And we also have a z in the numerator, which also comes from the sine angle. And the dq, remember, is eta dA. So I've plugged that in as well. And I've pulled out my k. My eta, though, I can't pull out, because remember, eta here is a constant. It's not a constant. It's a function of little r. Now, this is the point where if this was a uniform, and by the way, this should say e sub z, not e sub y. So I'm going to do this really magical thing in PowerPoint and say, fix it. And whoosh, it got fixed. Very magical. So now, again, if this was eta, if this was a constant charge density, eta would just be q over pi big R squared, and that would be it. And we would just plug in q over pi big R squared, we'd pull it out, and we'd evaluate this integral by u substitution, because our dA would be 2 pi r dr, but a u substitution would end up dealing with that 2r dr in there. So it would be a relatively easy integral, and we would be done. But in this case, eta is a variable. So still, you do the same thing as before. You plug in what eta is, and you evaluate the integral. On a test, or on the AP exam, evaluation of integrals is not where most of the points are, remember. Most of the points is for setting it up. So if you got this far, you would get most of the points on that problem. Now, evaluating the integral, well, really, what you should do after distributing stuff through and breaking it up into different pieces is you would look up each of the different pieces in an integral table. And so you would actually just go straight from here to the evaluation of the integral as revealed in the integral table and plug in the bounds and call it a day. What I'm going to do, though, is I'm going to show you how to evaluate these integrals, because a lot of people who are taking this course are either in a calculus course right now where they're practicing this stuff, or they're in multivariable calculus, where a lot of multivariable calculus problems have single variable integrals that need to be practiced evaluating, often using these types of tricks. So, I called these integrals f and g, after having pulled out the constants. So how about the integral f? Well, that's the easy one. I already forecasted that u substitution where the 2r dr would end up helping us out. So we're going to let a u equal a z squared plus r squared in the denominator there. So that just becomes u to the 3/2 in the denominator. And very conveniently, doing a du gives us a 2r dr. Substituting in our bounds, we would be now going from u equals z squared to u equals z squared plus big R squared. So there's our new integral for f. And that's the integral of u to the minus 3/2, which is just u to the minus 1/2 divided by negative 1/2. And u to the minus 1/2 is just 1 over square root of u. There's our negative there as well. And the negative 1/2 dividing by that gave us that factor of 2. We plug in our bounds, and there's our result for f. And we're just going to set that aside. In this case also, since we only want the magnitude of the field, it's safe to simplify square root of z squared to just z, since we want the magnitude of the field at some distance above the disk. So there's the evaluation of our integral f. Yay! What about g? That one's nastier. In fact, we're going to use multiple tricks here, both of which I think are really cool. So first of all, we're going to use integration by trig substitution here. We're going to let our original integration variable r be defined as z tan theta, where theta is just some angle of which you can take a tangent. Again, we're doing that. We did something very similar in the last video because we know that tan squared plus 1 is secant squared. Okay, so tan squared plus 1 is secant squared. Now, the derivative of tan theta is also secant squared. So at first it seems like, oh, that's going to be good. Things are going to end up canceling. But the thing is, we have different powers of these things. So yeah, we're going to end up getting a end up getting a z secant squared theta for our substitution for dr. So that'll become a z secant squared theta d theta. But we also need to plug in a z squared tangent squared theta right up there for that r squared as well. So after doing all of that and plugging in and using the fact that the denominator has turned into a z squared secant squared theta quantity to the 3/2, we pull out z squareds, which end up canceling. We get 3 factors of z in that denominator, which was raised to the 3/2 power. We have 3 factors of z in the numerator, so that seems nice so far. We change our bounds, since r is z tan theta. We say, okay, theta is the arctan of r over z, and that's a big R right there, because we plug in 0 at the bottom, we plug in big R at the top into our new expression. So great. We have the integral of tan squared secant squared theta over secant cubed. Some of those cancel, but we're still left with a tan squared over secant theta. Well, here's where we use that identity again. We use the fact that tan squared is secant squared minus 1. So it's like we used that identity one way to make the denominator easier. Now we're using the identity back a different way to make our new numerator easier. And the result of doing that gets you the integral of secant theta minus cosine theta. Well, cosine theta is easy. That's sine theta. We can deal with that. But what about that secant theta? There's a trick to that. The trick is you multiply top and bottom by secant theta plus tan theta. The reason this trick might come to mind, or at least a reason that it might come to mind, is you know that the derivative of secant theta is secant theta tangent theta, and the derivative of tan theta is secant squared theta. And knowing both of those, you're like, oh, the derivatives of both of those have a secant theta argument in them. So that might be part of the motivation for coming up with such a funny thing to multiply your secant theta by. So I multiply top and bottom by secant theta plus tan theta in hopes that some miracle will occur, extending from the fact that the derivative of each of these things involves a secant theta. Well, it turns out it does work, because the derivative of secant theta, after you distribute through the secant theta, the derivative of the secant theta in the bottom is the secant theta tangent theta in the top, the numerator. The derivative of the tan theta in the denominator is the secant squared theta in the numerator. In other words, the entire numerator is the derivative of the entire denominator. So now we do a variable substitution. Let v, we already let u be something else for evaluating f, so we're going to let v equal secant theta plus tan theta, such that dv is the whole thing in the numerator. So that just becomes the integral of dv over v, which is natural log of secant theta plus tangent theta. I've substituted back in for what v is, plus a constant for the indefinite integral. But this is a definite integral, and we have bounds of little r equals 0 to little r equals big R. So there is the evaluation of our integral, where I've changed my bounds already, since I had already done that trig substitution bit. And evaluating this using what you know about trigonometry, the secant of an arctangent is square root of z squared plus r squared over z, if your arctangent is r over z. The idea is that the r is the opposite leg of a triangle, the z is the adjacent leg of a triangle. So secant needs to be hypotenuse over adjacent. And then we still have this one, r over z. And secant of 0 is, well, 1 over cosine of 0, that's 1. Tangent of 0 is 0, but natural log of 1 is also 0. So what we're left with is this expression for our other integral, g. Yay! Now we have f, now we have g. All of this has been really fun. We could have just looked it up in an integral table. But now we plug stuff back in. Hey, that looks ugly. It turns out things cancel. Notice we have a 3 times 2 here, which is a 6. Oh, we already have a 6 right here. Wonder what's going on with this thing right here with our square root expression. Well, we have a 1 over r squared here, and we have a 1 over r squared there. Those cancel, leaving us with this expression for our electric field above the middle of a disk of charge, such that the charge decreases uniformly from the center of the disk to 0 at the edge of the disk. Wow, what a problem. Now, some comments on that last solution. It's possible to show that if you look at that natural logarithm expression, it can be expanded into a Taylor series. And after expanding this thing into a Taylor series and noticing that you get a couple of cancellations, what you're going to be left with is kq over z squared. So that actually does tend toward the fact that the electric field goes as kq over r squared as r becomes large, or in this case as z becomes large if you're going away from the middle of the disk along the axis of the disk. So in other words, it makes sense. Actually showing that with that Taylor series expansion is going to be left as an exercise for the student. Now, the electric field of an infinitely charged plane. Well, going back to our previous situation, at the point where we plugged in our eta is equal to that b expression times big R minus little r, well, if it's an infinite charged plane, but it's of uniform charge distribution, well, eta would just be q over pi big R squared, and the integral would be easy to evaluate. And what you would do from there is you would have an expression that's in terms of the radius big R of your disk, and then you would let big R run off toward infinity so that your disk turns into an infinite plane. That is done in many, many sources, so I'm not going to redo that here. You can check some other YouTube video, you can check your textbook. What I'm going to do here is get the same result using a different method. Instead, I'm going to pretend that, well, we're still going to have the plane being uniformly charged, but what we're going to do is a situation where we consider a plane being a whole bunch of little wires that are strung together, and find the electric field contribution of each wire, and then integrate those results from x equals negative infinity to positive infinity. So we're going to say that our field point is some point z above the plane, and the plane extends infinitely in both the x and y directions. Why am I doing it this way when the other way is much easier? The reason I'm doing it this way is because a problem that you will occasionally come up against would be something having to do with deriving an expression for the electric field due to an infinite sheet, where the sheet extends infinitely in one direction, but not infinitely in both directions. In other words, where in this diagram, I'm saying that y is going into the page or into the screen, x is going left and right, while x is increasing, x is going to the right, and z is going up. Well, in an infinite sheet situation, it might have a thickness of, say, like 2x, but extend infinitely in the plus and minus y directions. So using the methods that we're going to show here, that is how you can deal with a situation where you have an infinite sheet rather than an infinite plane. So hopefully people don't end up getting scared sheetless on those types of problems, because we're about to examine how to deal with that. Because what we're going to do is we're going to assume that it actually is an infinite sheet, and then we're just going to let x run off toward positive and negative infinity at the end. So remember what the electric field is due to an infinite line charge. In other words, an infinitely long wire. It's 2k lambda over r, where r is your distance from the center of that wire, where the wire is assumed to be infinitely thin, or at least if it's not, that you are outside of the surface of the wire. If you're inside the surface of such a wire, that's what we would use Gauss's law to solve, and that'll be in the next chapter. So anyway, the electric field due to an infinitely long wire is 2k lambda over r, where lambda is the linear charge density. Now notice that if I'm doing that here, the distance r that my field point is from the perpendicular to the line, so to speak, the line of charge, is square root of x squared plus z squared, or for that, if you want to call it curly r, fine, but square root of x squared plus z squared. Okay, so I have that. How do I turn a lambda into an eta, or how would I express eta differently? So here's the idea. Lambda is equal to eta times dx. Why does that work? So why is lambda equal to eta dx? Probably the easiest way of thinking about it would be realizing, okay, eta is just dq dA, in other words, charge per unit area, so dq over dA, but dA is dx times dy. So if I multiply both sides by dy, I would just have dq dx equals eta times dy. Well, dq dx is called lambda. So lambda is eta times dy, and I can call my variable anything I want, so I just renamed it to x. Okay, so now that we have that out of the way, keep in mind that we only want the z component of our electric field because x and y components are going to cancel. So in other words, the z component of the electric field is going to be equal to what the magnitude of the electric field would be due to just the wire, times z over r. In other words, times the sine of the angle above the plane pointed toward the field point. And well, what's the sine? It's opposite over hypotenuse, or z over r, where r is the square root of x squared plus z squared. So plugging in everything, here is our infinitesimal electric field contribution due to this wire that is infinitely thin and has a known surface charge density. So I've plugged in my z over r, there it is right there. My E is 2k lambda over r. So there's my 2k, there's my r, and remember lambda we established was eta times dx. And my r is square root of x squared plus z squared. And I have two factors of that, so I just have x squared plus z squared in the denominator here. That's the contribution just due to this particular thing right here. So I need to add it up for all of them, and that's called an integral. So I'm just going to integrate over all of those types, all of those going from negative infinity to infinity. And I'm not going to bother with this whole dog and pony show of limit as x goes to negative infinity and infinity, stuff like that. I'm just going to call it integral from x equals negative infinity to infinity. Nothing funny happens in this integral. It doesn't blow up anywhere or anything like that. So this is what I would call a trivial trig substitution. You might even already just know from memory that the integral of this is z tan or z arctan x, but we're just going to show that. So let x equal to z tan theta. So dx is z secant squared theta d theta. The denominator ends up becoming z squared secant squared theta. So your secant squareds are going to end up canceling. Yay, the z squareds cancel. Our z's also cancel. Look at that. We have a z that came out already. We have a z in the numerator. We have z squared in the denominator. So those cancel. So there's our integral. It's a trivial integral. Just going from theta being negative pi over 2 to pi over 2. We got those bounds by saying that it was x equals negative infinity. Well, what value of an angle, what angle would happen such that when you take the tangent of that angle you get negative infinity? Well, that would be an angle of negative pi over 2. And then to get infinity, taking the tangent of that, well, you'd use pi over 2. So that's how those bounds come in. Okay, well, that's just variable evaluated from negative pi over 2 to pi over 2. So just pi over 2 minus negative pi over 2, that's called pi. So we got 2k pi eta. Well, here's the thing. Remember, k is 1 over 4 pi epsilon naught. And 1 over 4 pi epsilon naught is 1 over 2 pi times 2 epsilon naught. And the 2 pi's end up canceling. So all we're left with now is just eta over 2 epsilon naught for the electric field at a position z above an infinite plane of charge. Well, wait a second. Where is z in this expression? I don't see z in that expression. Z canceled, remember? There is no distance dependence. No matter how far you are above or close to an infinite plane of charge, the electric field is constant. At least the field strength is constant. If you're above it, it's going to be pointed up. If you're below it, it's going to be pointed down, assuming that the charge distribution itself is positive. So, including all possibilities, the electric field vector would just be eta over 2 epsilon naught times z over absolute value of z, or if you prefer, z over square root of z squared times k hat. And of course, it's the same result that you would expect where they took it for a uniformly charged disk and let r run off toward infinity. But now you can use the same method and do it if x isn't negative infinity to infinity, but say x is negative L over 2 to L over 2. The method would still work. It's just that things wouldn't cancel quite as nicely, and you actually would have a z dependence. So again, yeah, it's independent of distance. Why it's independent of distance, at least physically speaking, getting some physical intuition of this, I think a good correct understanding of this would be imagining a cone kind of spreading out from the point where you want to know the field toward the plane. And with that cone, as you increase, if you were to multiply your distance above the plane by x, the influence of the charge that's in that plane would go down as 1 over x squared. But as you multiply your distance above the plane by x, you end up getting x squared times as much charge in that cone. So the amount of charge that you get ends up, or at least the relationship for the amount of charge that you get, ends up canceling the relationship for the effect, the influence of that charge. So that's how you can kind of explain that intuitively, so to speak. So increasing your distance is canceled by the fact that you end up getting more charge in your window of view. Now, beware, you might end up coming across some incorrect explanations about this. For example, if you hang out on the wrong street corner or some of the shady areas of Vienna, Virginia, some people might end up coming across you and surrounding you, and you see they're wearing these heavy, big, baggy clothes, and they have their hoodies up in the middle of the summer, and from their accents you realize that they might be Russian KGB, former KGB that is, and they start whispering to you, and they say that, "Hey Mac, this independence of the fact that r goes to an infinity is because there is no scale for distinguishing near and far, and every point is close to a disk of infinite radius." And then after that, they might end up trying to sell you like Madison High School bumper stickers or season tickets for the Philadelphia Phillies or something like that. But don't listen to these people. There's a flaw in this argument, a big flaw in this argument. So at least one of the major flaws is the fact that it's like, well, if this argument worked, you could use the same argument and say that there should be no distance dependence for the electric field away from an infinite line of charge, because then there would be no concept of closeness in that type of situation. But we already established the fact that the electric field due to an infinite line of charge is 2k lambda over r, where lambda is the linear charge density, and there's that r there that you just can't get rid of. So beware of arguments having to do with infinite charge distributions. An application of this type of thing is the parallel plate capacitor. This is a very common application of this, and we'll end up getting more into this when we talk about capacitors in more detail after we get into the concept of the electric potential. But in any case, a parallel plate capacitor is a situation where you have one plate given a positive charge and another plate given a negative charge. And these plates are close enough together such that the distance apart is much smaller than either of the dimensions of the plates. So you can effectively think of them as infinite planes. Well, we just established that the electric field due to an infinite plane is independent of distance. So if one of them is positively charged and the other is negatively charged, if you go above the whole contraption, the negative electric field, or the electric field down from the negative plate, will cancel out the electric field up from the positive plate. Same thing happens if you go below the positive plate. The only place where that doesn't cancel is the fact that, well, if you're in between the plates, the electric field due to the positive plate from below will be pointed up. The electric field due to the negative plate above will be pointed up. So they will end up adding together in that case. And your eta over 2 epsilon naught, well, you get a factor of 2 of those, 1 per plate. So the overall electric field in the middle or between the plates of a parallel plate capacitor is going to be given by eta over epsilon naught times k hat, assuming that the positive plate is at the bottom and the z direction is up. I would actually recommend memorizing this, because this equation comes up a lot, particularly with multiple choice problems on the AP exam. So, some other notes. In truth, in reality, there's no such thing as an infinite sheet or an infinite plane. And as a result, in a real scenario, the field lines are going to kind of curve out and kind of repel toward the edges of the plates. We call these fringe fields, such that in a real situation the fields are kind of something like this. But notice that the magnitude of the field in between the plate is much bigger than the magnitude outside. So that's again something to keep in mind. Now, what about other 2D surfaces? So what if it was a thick slab instead of an infinite plane? In other words, what if it wasn't a plane, it was a slab, and it had some sort of volume charge density? Or what if you needed to deal with a sphere instead of a disk of charge? Well, we have tricks that we can use for those. You could use multivariable calculus with some of those, but the tricks are going to show us that there is something called, well, the tricks combined with Gauss's theorem, which is often called the divergence theorem, end up showing us in the form of Gauss's law that we can actually turn these things into one-dimensional integrals. And we're going to have a lot more to say about that in the next chapter discussion. Now what about the motion of a charged particle in an electric field? So a charged particle in a uniform electric field will move with constant acceleration, because if it's a uniform electric field, that means there's going to be a uniform force, so F equals QE, and since F equals MA, that would mean that the acceleration will just be QE over M. So, practical application of this is that different fragments of DNA have different sizes, and so they will have different terminal velocities in a gel that has a constant electric field. So, gel electrophoresis, I hope I have not butchered that pronunciation, I've only read about it, is a technique of charging the DNA fragments and then turning on an electric field to sort out the DNA fragments by size with fluorescent markers, allowing those results to be determined. Now, a difference is that unlike a gravitational field, which always points down, the electric field can point in any direction. So that direction needs to be determined before you can actually figure out the direction of the acceleration. But other than that, the motion of a charged particle in a uniform electric field, assuming that it doesn't experience any other forces like the friction of a gel or something like that, is just going to be like projectile motion. So if you just have an electric field present and it's in a vacuum, a charged particle will move just like a massive object would move in a gravitational field if the gravitational field is assumed to be constant. Now, if your electric field is not constant, then just like with a gravitational field, you'll probably need to adjust and use calculus. But in any case, for these types of problems, you might need to brush up on your kinematics equations. But it's just kinematics, and that's kind of my point there. So there are also energy conservation principles that you can use for solving a lot of these types of problems, but we're going to get into that after we introduce the electric potential in Chapter 28. So something to keep in mind is that a lot of times when you have those problems, charges will be given in terms of a number of elementary charges. So you'll just have to keep in mind that when that happens, the total charge you have is equal to the number times the value of the elementary charge. Where remember, an elementary charge is defined to be positive, so the electron has a charge of negative lowercase e. So a negatively charged electrode is called a cathode. And physicists first learned to produce electron beams in the late 19th century, and they referred to those as cathode rays. And that's how pictures were produced in old television sets, which are often, basically they had a cathode ray tube that had electric fields that helped to direct the charged particles so that they would end up landing in different positions on a phosphorescent screen. So here's an example. Let's say you have an electron gun creating a beam of electrons moving horizontally at 33 million meters per second. Well, that's typical speed for an electron. It's over the 10th of the speed of light. But here we'll pretend that we don't need to deal with relativity. Our result will still be correct to within better than 1% at that speed. So in any case, the electrons enter a 2 centimeter gap between two parallel electrodes, where the electric field is 50,000 newtons per coulomb down. So which direction and by what angle is the electron beam deflected by these electrodes? So the point here is we want to find the final velocity vector. Direction of motion is given by the direction of the velocity vector. Well, we know the horizontal component. That's been given, 3.3 times 10 to the 7 meters per second. Question is, what's the vertical component? Initially, the vertical component is 0, but that vertical component is going to experience a change because of the fact that there's an acceleration due to a force. So once we figure out the vertical component, we can use the fact that the tangent of the angle is equal to the quotient, the ratio of the vertical component divided by the horizontal component. And here I'm using the angle as the angle below the horizontal. So v sub x is constant. V sub y, well, v vector is v naught vector plus a vector t. The x components are constant, well, because the x component of acceleration is 0. So v sub y is v naught y plus a sub y times t. So v naught y is 0. A sub y, well, Newton's second law, force equals mass times acceleration. So a sub y is the force divided by the mass. The force is given by F equals QE, and the electric field is pointed downward, so the force is going to be downward. So F equals negative E. It's negative E because it's an electron, and the electric field itself is pointed downward. So actually, overall, the force is going to be pointed upward. I meant to say the electric field is pointed downward, but the charge is negative, the field is negative, so the electric force is going to end up being pointed upward. So we have an expression for v sub y. V naught y was 0. Initially, it was going horizontally. The acceleration, we have that. So here's our expression for what v sub y is going to be in the end. And again, e sub y is negative. So delta x is v sub x times t. The reason we need that delta x is because the time that it's in the electric field has something to do with how big the area is. So that's our delta x. The area is 2 centimeters thick. So now we have our equation where we're able to relate our v sub y with that delta x. So again, there's where the t comes in. T is delta x over v sub x. So we plug the v sub x over the delta x over v sub x in for t, getting this expression for our v sub y in the end. Now we're finally ready to plug in numbers. And when we plug in our numbers, we see again the negatives end up canceling. So we get that v sub y is about 5.3 times 10 to the 6 meters per second. So first of all, the electron is deflected up because it's a positive v sub y. And the angle is given by the ratio of v sub y over v sub x and taking the arctan of that ratio to get the angle. And upon doing that, we find that the upward deflection angle turns out to be 9.2 degrees. Okay, So again, that's really what happens in a cathode ray tube, like what we mentioned before with the old television sets. Unfortunately, a lot of people in this generation do not have much of an appreciation for that, because now televisions and computer screens are liquid crystal displays or LEDs and stuff like that, and you don't have that type of experience. Now, what about a dipole in an electric field? So, a dipole, remember, is a situation where you have two charges that are equal in magnitude and opposite in sign. So what's going to happen if you were to place such a thing in an electric field? Well, it turns out it would not actually accelerate in a linear direction, but it would, at least potentially, get rotated such that everything's kind of in line with the electric field. So in other words, since it's getting rotated, that means that there is a torque acting on it. And it can be shown that the torque vector on such a dipole is equal to the dipole moment. Remember, the dipole moment is just equal to the size of one of the charges times a vector going from the negative charge to the positive charge, but the torque is going to be equal to the cross product of the dipole moment crossed with the electric field vector. So what does that do? Well, it ends up acting such that if there's an angle between the dipole moment and the electric field, this torque acts so as to decrease that angle. It's going to decrease that angle. And you won't have a torque at all if the dipole is in the same direction as the electric field. Now, if you were just to fix a dipole there, and well, or at least if you were to fix the middle of it there and just set it to in an electric field at an angle, the result is, yeah, it would decrease the angle, but then by momentum, conservation of momentum, it would kind of keep going until it reaches the opposite angle and it would oscillate back and forth. That's that type of oscillation problem, and finding the frequency of such an oscillation is something that occasionally comes up on exams. So in this picture, what is the direction of the torque on this dipole? So is the direction right, left, up, down, into the page, out of the page, or kafefi? Now, remember the torque is P vector cross E vector. So P vector is pointed up and toward the right. E vector is pointed toward the right. So you do that cross product. The way I do it is I kind of point the fingers of my right hand in the direction of the first vector, which is up and toward the right, and I make it so that as much as possible my palm is facing the direction of the second vector. So when I do that, my palm is, at least it has a rightward facing component. In other words, it's not facing into the page or out of the page or anything like that. But when you do it that way, your fingers on your right hand facing in the direction of the first vector and your palm as much as possible facing the direction of the second vector, your thumb on your right hand will be pointed in the direction of the torque, or the direction of the cross product in general, the torque in this particular situation. So that's going to be into the page. Into the page. So choice E. So just some things to keep in mind. Don't forget to multiply by the electric field when you're performing calculations, say like of angular acceleration, when you're that involve electric dipoles and electric fields. And if it's a non-uniform electric field, keep in mind that first the dipole will rotate and orient itself in the direction of the electric field, and then it's actually going to feel a net force, because if the electric field is non-uniform, one of the charges will be in a region of different electric field than the other charge after it's oriented itself, rotating in place. So at that point, the thing is going to end up moving. So that's something to keep in mind. So here's an example. Derive an expression for the oscillation frequency of an electric field dipole of dipole moment P and moment of inertia I for small oscillations about its equilibrium position. Well, the equilibrium position will just be in the direction of the electric field. So we're going to use the fact that torque, well, we have the equation for torque. It's given to us as P vector cross E vector for the torque on a dipole. But torque in general, back from kindergarten physics, is given by I alpha. In other words, F equals ma, force equals mass times acceleration. The rotational analog for that is the rotational version of force, torque, is equal to rotational version of mass, called moment of inertia, times rotational version of acceleration, that is angular acceleration. So tau equals I alpha. So apparently, P vector cross E vector is equal to I alpha, where alpha is the angular acceleration. And again, keep in mind that this is going to act so that the angle itself is going to be decreased. Well, that since the cross product, the magnitude of the cross product, is just equal to the product of the magnitudes of the vectors times the sine of the angle in between the vectors, this P cross E becomes PE sine theta. And I slapped a negative sign in front of that because this torque is going to act to decrease theta. So that angular acceleration is going to be negative PE sine theta over I, after dividing both sides by I to solve for alpha. So there's the magnitude of the angular acceleration. Or, writing it like this, alpha plus PE sine theta over I is equal to 0. I just moved all my terms to one side. Well, alpha is the second derivative of the angle, the second time derivative of the angle. In other words, alpha is d omega dt, and omega is d theta dt. So a common shorthand is that a time derivative of a variable is denoted by putting a dot above that variable. So alpha is the second time derivative of the angle theta. So great, we have that. All right, what do we do with this? Well, the next realization is that we were told that we were dealing with small angle oscillations. And at small angles, sine theta is about equal to theta, assuming we're expressing everything in radians, which we should be. So using that, we have that theta double dot plus PE over I theta equals 0. Let's see now. I know of a function whose second derivative is kind of equal to itself, just with a minus sign. In other words, just thinking like, okay, if I take a function, I need a function whose second derivative is the negative of my function times a constant, such that when I add them together, I get 0. Because there's my function, there's the second derivative of my function. Theta and theta double dot. So sines and cosines act like that. Well, okay, what must be the coefficient inside the sine in front of my variable? Or inside of my cosine, whatever. Well, it needs to be equal to the square root of the thing that's in front of my variable, such that when I take two derivatives, I end up getting it back twice by the chain rule. So, in other words, taking the first derivative, I get a factor of square root of PE over I from the chain rule. Taking the second derivative, I get another factor of that. So I end up getting 2 factors of square root of PE over I. So apparently, the thing that's inside of my sine or cosine that's multiplying my t is equal to square root of PE over I. Well, what is that thing? That's called the angular velocity. Or sorry, not the angular velocity, but the angular frequency. The angular frequency. I don't want to confuse that omega with other omegas, but it's the angular frequency of oscillation. It's not the angular velocity, but the angular frequency of oscillation. So be real careful on that. Well, how do you relate frequency with angular frequency? Well, normal frequency is 1 over 2 pi times angular frequency. So there we have our frequency of oscillation. So things to keep in mind. Just a reminder about how we got that minus sign. We kind of thought of it as like, well, the torque causes the angle to decrease. Here's another way of thinking about it. How is this angle defined? Well, this angle is defined as the angle from the electric field vector to my dipole moment vector. But that's not what I want. The torque equals P vector cross E vector. Well, the angle that I need there needs to be the angle from the dipole moment vector to the electric field vector. It's different. Angles can be positive or negative. So the fact that the angle theta in this picture is defined as the opposite as the angle theta going from P to E, that's another way that you can think of as picking up a minus sign. In other words, when you have C vector equals A vector cross B vector, the angle goes from A to B, not the other way around. But in the picture, it goes the other way around. So that's been a long discussion, but that finishes up our discussions of calculating electric fields due to charge distributions without using Gauss's law. After this, in our next set of videos, we are going to use an extremely useful mathematical trick to allow us to calculate electric fields due to certain types of charge distributions that exhibit very nice degrees of symmetry. So, until then, leave comments and questions in the comments bar on YouTube, and thank you for watching.